We can also show the inverse of a linear transformation, but this is only possible if the matrix represented by the linear transformation is also invertible. That's the task that we're going to do here. We're going to come up with the inverse of the linear transformation using a certain matrix that was taken away, or taken from rather, the given linear transformation. To do this, we are going to structure a certain matrix A as mentioned, okay, which is the standard matrix for T in this form. Take note that this is a, okay, we have here the transformation from R2 to R2. So we are expecting here a 2 by 2 matrix, 2 by 2 matrix, because this is from R2 to R2, okay? So that's again R2 to R2. In short, our matrix A is a 2 by 2 matrix, the standard matrix of this linear transformation. We are going to use this one here, since we know that this is a 2 by 2 matrix, hence there are two columns. The first column would be for the coefficients of x, the second column would be the coefficient of y. So our first entry is x plus y. So you have 1x plus 1y. Okay? As for the second, you will have x minus y. That means you have 1x minus y. This is now the standard matrix for the linear transformation T. The goal here is, once, or from this one here, once we can establish the inverse of A, in short, it is invertible, or the matrix is invertible, and we could again come up with a standard matrix of, what do you call this one? A. This is automatically will connect now, meaning that T is also invertible. And if this is invertible, we could come up with a certain linear transformation, or the inverse of the linear transformation of T. So that's the process. So since this is a 2 by 2 matrix, we know that the inverse of a 2 by 2 matrix, according to one theorem in our previous discussions, is equal to this form: 1 over our determinant, meaning AD minus BC, times this form. We have D, A, negative B, and negative C. Okay, that would be the inverse of a 2 by 2 matrix. Okay, so here our A is actually equal to 1, B is 1, C is 1, and D is negative 1. So the inverse of A is equal to, okay, you will have here, you will solve first the determinant. That's solve first AD minus BC. That's A, 1 times negative 1 minus 1 times 1. So that's negative 1 minus 1. AD minus BC is negative 2. Okay, so you will have here 1 over negative 2. Okay, that's the process. Then you have here D. So negative 1 here. Your A is 1. Negative of B is negative 1. C is negative 1. So we have negative C, which is negative 1 as well. So with this, our inverse, the inverse of the standard matrix of A, which is also the standard matrix of our invertible linear transformation of T, is equal to, we have positive 1/2, positive 1/2, you have positive 1/2 as well, and you have negative 1/2 here. Okay? In short, A is invertible. Okay? A is invertible. In short, T is also invertible. How do we come up now with a linear transformation for this? This is now the process of, after knowing the inverse of A, the process now is we're going to multiply our inverse with a certain vector V. Okay? In this case, our vector V has components x and y, so it would be with the same variables. In short, we have here the inverse times your V, which is x and y. Or you could automatically write here the inverse. Let's write the inverse here. You have your inverse, meaning 1/2, 1/2, 1/2, negative 1/2 times x, y. Okay? Is equal to something. That's now the result for this form here. So we have here 1/2 times x. So you have 1 half x, 1 half of y, so plus 1 half of y. Okay? Because this is a 2 by 2 matrix and you have here 2 by 1, so you're expecting a result which is 2 by 1. This is just one entry, okay? Then 1 half of x, you have 1 half of x. Then negative 1 half of y minus 1 half of y. Now, let's use some spaces here. Pardon for this, I still have another form here. So let's use some spaces here at the bottom. Okay, what do we do with this then? Okay, this is now the result. We are now going to come up with this one here, the inverse of our linear transformation. After this, the first entry here will be the first entry of your transformations. You have 1 half of x plus 1 half of y, then 1 half of x minus 1 half of y. Or if you would like to, you could always since we have 1 half and 1 half, factor 1 half, so you have x plus y over 2, and you have x minus y over 2. This is the inverse of the linear transformation here described on our first given. So the inverse of linear transformation defined by this is this one here, and we're able to solve that by again starting with our inverse of the starting with our standard matrix, inverse of the standard matrix. We get this, and then the entries of this product will become your entries of your vector. So this is in vector form. Now let's do the same thing on the second. Our standard matrix here, again xy, that's a 2 by 2 matrix. X, 1x plus 2y, then 1x minus 2y. Then we are going to show its inverse, which is again represented by this AD minus BC. This is only to clarify, this is the process in solving for the inverse of a 2 by 2 matrix. If it's a 3 by 3 matrix, then we're going to use another method to that. Okay, so our A here is 1, B is 2, C is 1, D is negative 2. So the inverse of A, let's solve first AD minus BC to see if this is really invertible. Okay. So A1 times negative 2 minus 2 times 1. You have here negative 2 minus 2, negative 4. By the way, if as a review, if AD minus BC is 0, then this is undefined. Hence, our matrix A, our standard matrix A is non-invertible, and that would mean our linear transformation T is also not invertible. But here you have negative 4 times D, which is negative 2, negative of B, so negative 2, negative of C, negative 1, and you have here positive 1. So the inverse now is equal to negative 2 times this, negative 1 at 1/4, so you have positive 1/2. This is also positive 1/2, positive 1/4, and negative 1/4. Okay, when you multiply 1/4 scalar to all the entries, again positive, 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 negative. Now this again, after we have our inverse, we're going to multiply this with a certain vector, in this case again represented with x and y. So you have here 1/2, 1/2, 1/4, negative 1/4 times x and y, which will give you 1/2 x plus 1/2 of y, then 1/4 x minus 1/4 of y. Okay, so with this, our inverse of our linear transformation T is now the entries here. So you have 1/2 x plus 1/2 of y, and 1/4 x minus 1/4 of y, or again combining them or factoring 1/2. So you will have here x plus y over 2 and x minus y over 4. This is now the inverse of this second linear transformation. Again, the process involves standard matrix of the linear transformation, checking if it's invertible, in short, getting its inverse. If we have that, we need to provide with this, and the result would be the entries of your inverse of your linear transformation. Thank you very much for watching.